So, well, this is the demonstration of universal vibration tester trainer. And we have got some electronic panels in the first row. That is the instrumentation power supply. This is a power supply panel, in fact. And also, there is a DPM given. DPM is given for speed. Less than 2000 RPM and for greater than 2000 RPM. NC stands for not connected. It is only for 1 and 2 position. We have got AC AC supply we will get from here if we switch on this MCBs. And second thing, we have got DC power supply here and a variable power supply 0 to 12 volt DC. If I vary this, the fan, the motor will rotate. I'm giving 0 to 12 volt DC to this thing. We have got a 12 volt motor here. And the second panel is a sensor signal conditioning panel. It is for speed calibration. We need to understand that is frequency to voltage actually. So to understand speed, we need this sensor signal conditioning panel. The third panel is sound vibration sensing transducer panel, and all the switches whatever given here should be at the top, that is enable. 3 position slider switch SW3 is given here, that should be also top. 3 position slider switch SW4 on top, and this is the Doppler. We are going to select SW2 to Doppler. And one important question is that what are the power supply required to operate this panel. So everything is inbuilt, 12 volt, minus 12 volt, 5 volt. It is all given through this FRC cable from this power supply panel to the neighboring panels. FRC. This is a 20 pin FRC cable. And finally, we have got one electronic panel, that is a computer interface panel. There are 4 ADC channels, channel 0 to channel 3. And we have selected channel 1. This is the output. From Doppler Hall amplitude, it is connected to channel number 1 and it is connected to PC. See, it is connected to the CPU right now. And this is the entire mechanism. On the bottom side, we have got a spring, a motor, and this is a wheel. And one important question you will ask me, where is the Hall sensor? Then this basic thing that I'm holding, this is the Hall sensor here. Hall sensor. So let's begin the experiment. I've got a manual with me. And the experiment that I'm going to conduct is study of compound pendulum and determination of acceleration due to gravity and radius of gyration. And this is the page number 445. The entire setup is given here. We have got a compound pendulum Hall sensor, and it's going to MIT4 panel. And after that, we have got a CIP panel, computer interface panel, and virtual workbench, that is the PC software that I'll be using. So here we have got a virtual workbench 11.4. It is open. So this is the wiring schedule. MIT4 socket number 4 is connected to CIP2. So basically this is connected to this one, and you will ask me what is this. MIT4 is here, modular instrumentation trainer socket number 4. So B4 is here, and second, and make the mechanical arrangement as shown in figure. Number 2, connect Hall sensor to MIT4 panel using 6-pin DIN connector cable. So everything is connected here. All these things I have connected is a cable. Number 3 is open virtual workbench software on PC screen. So well, yeah, and this is the way. We have to make it on start graph, and the graph will start plotting, and this is the pendulum. Yeah, and look at the graph, see the graph. So in the manual also they have given a graph of compound pendulum for 30 centimeter distance from CG. So this is the graph, a sample graph we have provided. And so the next page we have got an observation table for compound pendulum, serial number, distance from CG in centimeter, number of samples for 20 oscillations, trial 1, trial 2, mean, and the last column is time period that we have to calculate. So keep knife edge A on upside. keep knife on this one. And the last thing is we have filled this one in the instructor's guide. I'll show you that one. So the table number is, this table number is 4.2.1. so I'll show you here this one. There's a manual that I'm holding of 4.2.1, so it will be somewhere here. So this is that 4.2.1 observation table for compartment. Everything is filled in our manual. For distance from CG, centimeter 30, we have got trial 1 249, 249, 249, and the time period they have calculated. And one so the conclusion of this experiment is, from the above experiment, it is observed that the experimentally calculated value of G is found to nearly equal to theoretical value of G. This is the conclusion of the experiment that we have done. Thank you for watching this video. Thanks. So, well, this is the second part of the universal vibration tester experiment. Earlier I have already mentioned one by one panel, whatever is used in this first row. That is, we have got a EMT8 power supply panel. Second one is a sensor conditioning panel. This is used for speed. To understand the speed of the motor, we have given a 12 volt DC motor here. To understand the speed of the motor, we have used a sensor conditioning panel. It is a calibrated one. The third one is a vibration sensing transducer panel, MIT4. And all the switches like switch 1, switch 2, so many switches are given, and it is kept at the up position, top position. For example, SW1 is kept at enable position. Switch number 2 is kept at Doppler. And switch number 3 is kept again at Doppler effect, like that. And it's a vibration sensing transducer panel. Finally, we have got a computer interface panel. I have connected it to the PC USB port. From here, it is a 25 pin connector here, and there are 4 ADC channels from channel 0 to channel 3, which will accept 0 to 2.5 volt in this computer interface panel. We have used channel 0 and channel 1. Channel 2 and channel 3 is left. So please see the connection. Channel 0 is connected to this EMT8 speed socket, that is socket number 6, and this is the ground. And finally, we have got this experiment study of undamped forced lateral vibration of the beam, both end held. This is the diagram actually, and we have got all the electronic panels on the top, and this is the 12 volt DC motor. And here we have got a Hall sensor. This is the Hall sensor part, and here there is a magnet. See, this is the magnet part, Hall sensor, and this one is called as rectangular MS bar 25 into 12. This one, it is written here rectangular MS bar, and it is not that fully tight. It is not fully tight. We haven't, and magnet is there, and this is called as a weight hanger. It is mentioned here, weight hanger, as per the picture. Now this is the block diagram of the experiment, that is study of undamped forced lateral vibration of the beam, both end held. We have got a beam lateral vibration, Hall sensor, speed sensor, etc. From here it goes to a MIT4 panel, from there it goes to CIP panel, and from here it goes to virtual workbench PC base. So this software, that is called as virtual workbench 11.4 software, it is connected. Green indicates that the connection is proper with the trainer. Next is, it goes to EMT9 panel vibration, vibration frequency speed. EMT9, yeah. And this is a wiring schedule we have got. We have done, our engineers have done the wiring schedule as per this one. And there is a big procedure also given, a very simple procedure we have given here. And here table 3.4.1 is data logger parameter setting for undamped vibration of beam, serial number, speed, channel 0, speed, RPM, all these things we have already set. And this is the graph of undamped vibration of beam, which we will get it here. this one, this one, and yeah, this is in percentage. Here it is percentage, and here it is written as RPM. This is actually RPM, and this is in percentage. And finally, you will ask me, what is the table that we are going to? Yeah, the table is observation table for undamped vibration of beam. Serial number from 1 to 12. Speed is channel 0. Sorry, speed is connected to channel 0. As I have already told you, we have used 4 ADC channels. It is connected to channel 0, and speed RPM is equal to, that's the calculation part. Speed channel 0 percentage into 20, amplitude percentage. Conclusion of this experiment is, from the above experiment, it is observed that for the beam, amplitude of vibration is maximum at around 1140 RPM. Yeah, we have got an instructor's guide also. You will ask me whether it is filled. Yes, every answers, every observation table is filled. 3.4.2. This is done. I'm taking it 3.2.2, and this one is your 3.4.2. This one. See, every observation table is filled at the back side of this manual. Table 3.4.2, like speed channel 0, speed RPM, that's a calculation part, and amplitude in percentage. Yeah, we are going to do the experiment now. Yeah, we'll make it on, and we'll spin this motor first of all. This 12 volt DC motor. I'll vary. Yeah, 500 RPM. We are going to set it, and this RPM we will observe it here because we have kept it the first position, and it's approximately 500 RPM. It's spinning at 500 RPM. Now we'll go to the virtual workbench.
Click read.
Click read data, and we are getting this one. Serial number is there 12, and 52.6. That reading 525.6. That is the speed RPM. Next reading, my engineer will keep it somewhere 800 RPM. 800 RPM, and we have to just click this read data. So it is showing around 760 RPM. Yes, 760 RPM, and speed channel 0 percentage, that is 38.039, and amplitude in percentage is 2.5, 2.3. The next reading, we are going to keep it around some 1000 RPM. So just it is around some approximately 1000 RPM, 964, and 48.325. And the amplitude in percentage is 17.255. The next reading we are going to take is around some 1387. That is the, and I'll click it here, read data. So 1349 is the RPM, and speed channel 0 percentage is 67.45. We are increasing the speed now. I'll check it once again. Read data. It is 1686 is the RPM now. Yeah. So based on that, now we are clicking the graph, smart graph. The vertical.
graph आएगा ऐसा बोलो कर.
We'll get a graph on this one. The data profile we have mentioned as spring mass system, and serial number, speed channel 0, speed RPM, and amplitude in percentage. Maximum position of this part, the RPM, the motor RPM is 1718. It's showing. Here also I have clicked it. It is approximately 1694, and we will check the graph here. And this is the graph. Just click this graph. This is a smart graph, virtual workbench 11.4. After taking this data logger, just click on this. Just click on this graph. You will get a graph like this. So I have got a manual. And is the graph that we have. That was a sample reading we have taken as per the procedure. Graph of damped vibration of beam with the damper. So in this way we have completed the experiment. The name of the experiment is damped forced lateral vibration of the beam with damper. Thank you.
और कौन सा एक्सपेरिमेंट किया बताओ.
So well, this is the third part of universal vibration tester trainer. We have got all the electronic panels has been already demonstrated. Like we have got instrumentation power supply, multi-channel DPM. We have sensor conditioning panel to understand the speed. The speed will be displayed on this DPM. The third is sound vibration sensing transducer panel. And the fourth, we have got computer interface panel. All these things have been discussed in the first part of our video on universal vibration tester. Right now, I'm going to demonstrate study of Cater's pendulum and determination of acceleration due to gravity. So we have this particular arrangement. I have balanced it. Actually, here it is weight. This is called as wedge. These are weights placed at different A and B side. Here we have got, this is called as nylon weight. As per the manual, it is written very nicely, nylon weight on the right side, and onto the left side I have got MS weight. The connection also I have done onto this panel, like wiring schedule, everything is done. So the balancing technique we have to follow here, I have done it very nicely here, and after balancing it on the wedge, we have to take the scale. It's not balanced right now. I have disturbed it actually. See this thing, it's like this, and after balancing, we have to take this distance from here to here. So in centimeter, up till here we have to take the distance that will be in centimeter, and after that we have to place it so well, this is called as the pendulum hanger, and I have placed it in this way. The computer is on, and here there is a Hall sensor, and magnet is also nearby. The magnet, this is the magnet, and it will detect. Now we are going to give oscillation. Yes, we'll give oscillations. It will continuously move, and we will check the graph also. Yeah. Exactly. That's the way we have to fit onto the pendulum hanger, and there's a magnet here. Yes, this is the way. And please check the graph. So virtual workbench 11.4 version, that is the software we are using, and graph number, this is a smart graph, and we are getting the graph in this way. So as per the manual, we have got the observation table. This is the experiment that we are performing, that is Cater's pendulum, and we have got a 4.3.1 observation table for Cater's pendulum, serial number, 5 readings they have taken, number of samples for 40 oscillations. Knife edge A upside, NS1, knife edge B upside, NS2. The third column is knife edge A upside, time for 1 oscillation, and in this way. So this is the graph. This is a sample graph that we got as per this manual. That is graph of Cater's pendulum. Time for 40-second oscillation is equal to 473 samples. So the samples are in this way. At the bottom side, we have got samples. Onto the x-axis, we have got samples, and here we have got And finally, we have got a conclusion that I will read for you. From the above experiment, it is observed that the experimentally calculated value of G is found to nearly equal to the theoretical value of G. So this completes the demonstration of study of Cater's pendulum and determination of acceleration due to gravity. Earlier demonstration was study of Cater's pendulum and determination of acceleration due to gravity. That was already, we made a video demo. And now I'm going to show you study of torsional pendulum to determine moment of inertia and rigidity modules of material. So this is the mechanical setup for torsional pendulum. We have used 100 gram weight. This is the 100 gram weight at the outer portion as per this diagram. We can now, one question will arise that can we put it inside? Of course we can do that also, and we can do our experiment. It's a 100 gram weight placed at the outer portion or the outer side. And yeah, and this is the connection we have got. That connection I have already done it, and there is a procedure given as per the manual, and we have to just keep like this force, and it will keep on rotating, it will keep on oscillating, and this is the graph that we get. Please see the manual. That is graph of torsional pendulum. This is the graph. Samples are the bottom part, the x-axis, and here onto the upside we have got channel 1. I have connected, actually, please see here, I have connected to channel 1. There are 4 ADC channels. I have connected to channel 1. ADC channels will accept from 0 to 2.5 volt. All these ADC channels, and this is the graph that we get. The conclusion of this experiment is, from the above experiment, it is observed the experimentally calculated value of moment of inertia is found to nearly equal to theoretical value. And see, please see this observation table for torsional pendulum. We have got serial numbers, position of mass. Without mass, we can do trial 1, trial 2, trial 3, mean, number of samples for 10 oscillations they have taken, and time for 1 oscillation. And all the things that like T0 time period without mass, T1 is equal to time period with mass at close, all things are being mentioned in this manual, page number 4-18. And this is the observation table for torsional pendulum and without mass. Without mass means we have to remove this 100 gram weight, just to see. And I've got Allen key with me, and I'll just remove it this way. Just I'll loosen this one, and exactly like this. And I have got Allen key, and without Allen key also I can do it. I can manage it in this way, without mass. And second thing is masses at closest distance. Closest distance means we will be using this one. This will be using and will be tightening in this way. Yeah. And with the 100 gram weight, I'm keeping it at the closest distance. Exactly. And in this way. And the third one we have already done, that is masses at maximum distance. I have to keep the weight here, this side. So in this way we can take the 3 different readings: without mass, masses at closest distance, and masses at maximum distance. This ends the demonstration of torsional pendulum to determine moment of inertia and rigidity modules of material. Thank you for watching our video. Bye.